Welcome to this session. In this session, we are going to discuss the question number 9 from the chapter 1 of metric spaces. So let's see the question. What does it say? So let capital X denote the set of all real sequences and let small x equal to xi, I is greater than or equal to 1, small y is equal to small yi, I is greater than or equal to 1, be arbitrary elements in capital X. We are defining the function d of x comma y as summation k is equal to 1 to infinity 1 by k square minimum of modulus of xk minus yk comma 1. Now we have to prove that x comma d is a metric space, and if x and n greater than or equal to 1, which is basically x I n I greater than or equal to 1, n greater than or equal to 1, be a sequence in capital X, we now have to show that x n converges to x in capital X comma d if and only if xkn converges to xk for all k. So this is what we have to show. Now we know that for a set to be a metric space with respect to a function, it has to satisfy four properties, and the four properties are: d of x comma y should be greater than or equal to 0 for all x comma y belonging to capital X, d of x comma y equal to 0 if and only if x is equal to y, and d of x comma y is equal to y, d of y comma x, that is, it should be commutative. And then there comes the triangle inequality: d of x comma y should be less than or equal to d of x comma z plus d of z comma y. So first of all, let's see what basically x is. X is a real sequence. Okay, so the terms of x would be like x1, x2, so on and so on. Alright, now y would be also be like y1, y2, so on and so on. So this is basically a sequence of real numbers. Now what's xk minus yk? Xk minus yk is nothing but basically x1 minus x2, x1 minus y1 or x2 minus y2, so on and so on. So what's basically summation of 1 by k square, k is from 1 to infinity, minimum of xk minus yk mod comma 1. This is basically sum of 1 by 1 square minimum of x1 minus y1 comma 1 plus 1 by 2 square minimum of x2 minus y2 comma 1 plus so on and so on. Alright, so this is what does the function d looks like. So firstly, we are clear about the elements. What does the elements of capital X looks like? Alright, then we are clear about the function. Now we will show that d of x comma y is a metric, or more precisely x comma d is a metric space. Alright, okay, now let's move forward, and now we will try to prove all the four required properties for a function to be a metric on a set, or a set with respect to a function to be a metric space. Alright, now let's see the question once again. This is the question. I hope we are clear about it, and now we will move forward, and firstly we will try to prove that x comma d is a metric space, which is a very easy task. Let's prove this. Alright, the first property is, alright, we have to show that d of x comma y is greater than or equal to 0. I am extremely sorry for this technical glitch. Just give me a second. Alright, d of x comma y is greater than or equal to 0 for all x comma y in capital X. Alright, now d of x comma y is equal to summation k is from 1 to infinity 1 by k square minimum of modulus of xk minus yk comma 1, and here the modulus of xk minus yk is greater than or equal to 0 for all k from k is equal to 1 to so on and so on, and 1 is strictly greater than 0. Thus, their minimum would also be greater than or equal to 0 for all k from k is equal to 1 to so on and so on. Now 1 by k square is strictly positive. Alright, since k is a natural number, 1 by k square is well defined and 1 by k square is strictly greater than 0. That's why 1 by k square minimum of modulus of xk minus yk comma 1 is greater than or equal to 0 for all k equal to 1 to so on and so on. If this is true, then that means what? That means all terms are positive, then their sum would also be positive, since the summation of not positive, non-negative, the summation of non-negative numbers is also non-negative. That's why summation k is from 1 to infinity 1 by k square minimum of xk minus yk comma 1 is strictly greater than or equal to 0, and this implies d of x comma y is greater than or equal to 0 for all x comma y in capital X. Alright, I hope this first property is clear to you. Now we will move forward with the second property, that is to show that d of x comma y is equal to 0 if and only if x is equal to y. Now consider, we are considering d of x comma y equal to 0. That means summation of k is from 1 to infinity 1 by k square minimum of mod of xk minus yk comma 1 is equal to 0. And from the previous property we have seen that each summand in this infinite sum is non-negative, and if the summation of non-negative terms is 0, that means each term individually have to be 0. This is the only possibility. Alright, so this means what? This means 1 by k square minimum of xk minus yk comma 1 is equal to 0 for all k. Now we will write that. Okay, now 1 by k square is strictly greater than 0, and in this minimum term 1 is strictly greater than 0, so this minimum term should be 0 first of all. Alright, first of all this minimum term should be 0 for all k. Alright, it should be 0 for all k. Now in this term there are two terms, one of them is non-negative, one is strictly positive, and their minimum is 0. Alright, so that means the non-negative term should be the minimum and that should be 0, since 1 can't be 0. Alright, so xk minus yk modulus is 0 for all k. This implies xk equal to yk for all k. This implies x is equal to y. Now let's see conversely, if x is equal to y, that means xk equal to yk for all k. That means xk minus yk equal to 0 for all k. That means their minimum should be 0 and that would be for all k. Then 1 by k square multiplying with this would also be 0 for all k, and if all the summands are 0, then their infinite sum will also be 0. That means d of x comma y is 0. So we have proved that d of x comma y equal to 0 if and only if x is equal to y. I hope this is clear to all of you. Now let's move to the third property, which is very easy to prove. This is the commutative property, to show that d of x comma y is equal to d of y comma x for all x comma y in capital X. Now d of x comma y is equal to summation k is 1 to infinity 1 by k square minimum of modulus of xk minus yk comma 1. Now modulus of xk minus y can be written as modulus of yk minus xk. This is because modulus of minus a is equal to modulus of a. Alright, so that means this is equal to summation k is equal to 1 to infinity 1 by k square minimum of yk minus x comma 1, which is nothing but d of y comma x. That is d of x comma y is equal to d of y comma x for all x. Alright, now let's move to the fourth property, that is in general called as triangles inequality for a metric, to show that d of x comma y is less than or equal to d of x comma z plus d of z comma y for all x comma y comma z in capital X. Alright. Now x is equal to xk, k is greater than 1, y is equal to yk, k is greater than or equal to 1, z is equal to zk, k is greater than or equal to 1. All of them are sequences of real numbers. Alright. Now let us see that the minimum, alright, the minimum of two numbers, minimum of xk, see, the minimum of a comma b is strictly less than equal to a, and minimum of a comma b is strictly less than equal to b. Alright, the proof is, if there are two possibilities, minimum of two numbers is either a or b. If this is a, then a would be less than or equal to b. That implies minimum of a comma b, which is less than or equal to a, which would be less than or equal to b. Alright, right? Minimum of a comma b is less than or equal to a, and minimum of a comma b is less than or equal to b. And if the minimum is b, then this is obviously trivially less than or equal to b. And since minimum is b, b should be less than or equal to a. That means minimum of a comma b is less than or equal to a, and minimum of a comma b is less than or equal to b. That means the minimum term we are having, which is minimum of xk minus yk comma 1. Alright, let's first of all, let's rub this off. Now we'll write, okay, minimum of mod of xk minus yk comma 1 would be less than or equal to mod of xk minus yk and less than or equal to 1 for all k, and this is less than or equal to 1 for xk minus yk for all k. Alright, just a sec. Alright, so this is what we have got. Also we know that minimum of mod of a plus b comma 1 is less than or equal to minimum of mod of a comma 1 plus minimum of mod of b comma 1. Alright, that means consider d of x comma y. Okay, before considering that, let's write, okay, so minimum of xk minus yk comma 1 is equal to minimum of xk minus zk plus zk minus yk plus minus zk. Alright, so this is less than or equal to xk minus zk comma 1 plus minimum of zk mod of zk minus yk comma 1. Alright, now multiplying 1 by k square on both sides, we get 1 by k square. Minimum of xk minus yk comma 1 is less than or equal to 1 by k square minimum of xk minus zk comma 1 plus minimum of 1 by k square minimum of zk minus yk comma 1. Alright, okay, so this implies if this is true for all k, then this would be true for the summation also. Alright, if each term is, if ak is less than equal to bk for all k, then summation ak would also be less than or equal to summation bk. Alright, so this implies summation 1 by k square minimum of xk minus yk comma 1. This summation k is equal to 1 to infinity 1 by k square minimum of xk minus yk comma 1 is less than or equal to summation let me rub this, summation k is 1 to infinity 1 by k square minimum of xk minus zk comma 1 plus summation k is 1 to infinity 1 by k square minimum of mod of zk minus yk comma 1 This implies this is what d of x comma y, and there what d of x comma z plus d of z comma y for all x comma y comma z in capital X. From all these four properties, therefore we conclude that capital X comma d is a metric space. Alright. Now let's prove the next part of this question that says, what does it says? It says let xn is a sequence in capital X to show that x n converges to x in x comma d if and only if xkn converges to xk for all k. So first of all, let us understand what is xn. Xn is a sequence in capital X. And what is capital X? Capital X is a set of all real sequences. That means a sequence is nothing but what? Okay, let us write. Firstly we will assume, okay, firstly let us suppose that xcan the converse if part is true. Okay, suppose that only if part is true, that is xcan converges to xk for all k 1 to so on and so on. Alright, now what is this? Let me clear this. Now xk is a sequence. What type of sequence? It is a real sequence. What is xn? Xn is a sequence in capital X. Capital X is a set of all real sequences. That means xn is a sequence of real sequences, and a set of real sequences converges to a element of capital X which is a real sequence. That means a sequence of real sequence converges to a real sequence if and only if the component wise sequences are converges to the component. That means x is a real sequence, so there are components x1 x2 so on and so on. Now xn consists of sequences. Alright, there are one sequence, second sequence, third sequence and so on. Now that means the kth component of first sequence, kth component second sequence, if we take elements like that way, we are taking what does xn look like? X1 x2 so on and so on. Now x1 itself is a sequence, itself is a real sequence, x2 itself is a real sequence. Alright, so x1 look like x11, x21 so on so on, x2 look like x12, x22 so on so on. Suppose we are taking the first component from each of the sequences, that is we are constructing the sequence x11, x12. So axis look like x1, x2 so on and so on. Alright, that's clear. Now if we are taking the kth component, alright, if we are taking the kth component, suppose the first component we are taking first component from the first sequence, first component from the second sequence, so on and so on, this will generate another sequence. Alright, they are all real sequences, so there each component by sequence is also a sequence in X. That means if we take the component kth component sequence, then this kth component sequence should converge to the kth term of small x. That's what this means. So x11, x12, x13 and so on should converge to x1, and similarly for its k, this should be true. Then only this xn would converge to x. This is an if and only if result. So I hope what does this means, what does the sequence in X means, and what does small x looks like, it is clear to all of you. I hope that I am trying my best to visualize this to all of the viewers. So let me know in the comment section if this is clear to all of you. While solving this question, this become a little hard for me also when I was trying to solve this question. So I am trying my best. Alright, so let's prove this. So we have to show this is true if and only if that is true. Alright, so we are taking that xn converges to x for all k. Firstly we are supporting that, and we will show that xn converges to x in x comma d. Alright, so let's move to that part. We'll move slowly and we'll try to clear each step in this proof. Alright, so let's prove this question. Alright, okay. Now xn converges to x. Alright, xn is a sequence of sequences. We have to remember that while solving the question. I am repeating again and again, xn is a sequence of sequences. X itself is a sequence. Xn is a sequence of real sequence. X itself is a sequence. Alright, let's prove this. Okay, firstly let us suppose that xk converges to xk for all k equal to 1, 2 and so on and so on. So the component wise sequences are converging to component. That means for every epsilon greater than 0, since there are sequences in R with usual metric, by the definition of usual metric convergence of a real number sequence, we can write for every epsilon greater than 0, the epsilon definition, that is there exists nk depending upon epsilon belonging to the set of natural numbers such that xkn minus xk is less than epsilon whenever n is greater than or equal to nk, and this is true for all k. That means for each k we are getting a nk and the sequence xkn converging to xk. Alright, now we have to show that d of xn x is strictly less than epsilon whenever n is greater than or equal to capital N, say. Okay, capital N. Sorry, this should be xn. Okay, alright. Let me correct it. Xn. Yeah. Whenever small n is greater than or equal to capital N forms for some capital N in the set of natural numbers. Alright. Now that means the summation 1 to infinity, let's say q. Okay, 1 q to infinity 1 by q square. Let's not confuse with that k, so we are writing q. Okay, q square minimum of xqn minus xq comma 1 is less than epsilon for every epsilon greater than 0. Alright, where epsilon greater than 0 is an arbitrary real number. You can add that step in front of the proof that let epsilon greater than 0 be an arbitrary real number. Alright, this is true whenever n is greater than or equal to capital N for some capital N in the set of natural numbers. Now we know that for each k this modulus term is less than epsilon for every epsilon greater than 0. So what we can do, we know this minimum term is less than equal for both the terms. We have proved that. Alright, minimum of a comma b is less than or equal to a and less than or equal to b. Alright, now this is true for each k. So we can take the supremum of or the maximum of nk and take a common natural number. Alright, but the problem is there are countably infinite number of nk. Alright, so taking a maximum would not be convenient. What we will do, we will break this summand, and we know that the summation q is equal to 1 to infinity 1 by q square is nothing but pi square by 6. This is the Bessel problem. Square equal to pi square by 6. This is the Bessel problem. Alright. Now we can take a very large p. Alright. For sufficiently large p, we can say beyond this p the summation would be less than epsilon by 2. That means beyond this p the summation will be very small. Alright, 1 by q square is decreasing sequence. Alright, we everyone know that the sum is equal to pi by 6. That means beyond some point this is very small. Epsilon by 2 is less than epsilon by 2, and before that the summation is nothing but pi by 6. Alright, so we can write that for sufficiently large p. Alright, I hope this is clear. For sufficiently large p the sum becomes beyond that very small, and before that it is actually equal to pi by 6, approximately equal to pi by 6. Alright, okay, now let's move to the next part. Alright, so for p, these p, so these p's are finite, so we can take the maximum of these n p's. Alright, that is in particular for epsilon greater than 0, all epsilon greater than 0 it is true. So in particular for 3 epsilon by pi square greater than 0, there exists nk belonging to capital N such that xkn minus xk is less than 3 epsilon by pi square whenever n is greater than or equal to nk. Alright, for all k, this is true for all k. So this is true for 1, 2 up to p. So let's term this p. Let's mark this 1. Alright. Now for a fixed epsilon greater than 0, we choose p in z plus or p in n such that the assumption is true, that is summation q is equal to p plus 1 1 by q square equal to less than epsilon by 2. Okay, I think I have made mistake here also, less than epsilon by 2, and okay, alright, less than epsilon by 2, and this is less than epsilon by 2, and before that the summation is equal to pi square by 6. Alright, this is equal to pi square by 6. Alright, this is pi square by 6, not pi by 6, pi square by 6. Alright, okay. Now let's mark this as 2. Now from 1 and 2, what we can write? Let's try to write this. We will consider d of x n comma x. Alright, we are considering what we have to prove. We have to show this less than epsilon. This is equal to summation q is equal to 1 to infinity 1 by q square minimum of xqn minus xq comma 1, which is, if we break this, xq equal to 1 to p 1 by q square minimum of xqn minus xq comma 1 plus q is equal to p plus 1 to infinity 1 by q square minimum of xqn minus xq comma 1. We have to be clear here. xqn, what is xqn? Xqn itself is a sequence, qth sequence in xn, and xq is nothing but the qth term in x. Now for the first time we can take less than or equal to xqn minus xq, and for the second term, second minimum, we can take this is less than or equal to 1. So this is what we are writing. Alright, now this is less than or equal to 1, and this is less than or equal to xqn minus xq. Alright, now this is strictly less than 3 epsilon by pi square. Alright, for this is less than 3 epsilon by pi square, and this is less than epsilon by 2 whenever n is greater than or equal to n. What is n? N is the maximum of n1, n2 up to np. Alright, finitely many, so we are taking the maximum. Alright, now 3 epsilon by pi square is constant, this comes outside, and the summation is pi square by 6. Alright, this is what we are doing. We are taking this maximum of the finitely many terms from this. Alright, okay, let's do this. Okay, you are clear how we are taking the maximum. Alright, so for pth term up to pth term, this is what we are taking. Alright, now this is 1 by q square, summation is equal to pi square by 6. So this is equal to pi square by 6 into 3 epsilon by pi square by 6 into 3 epsilon by pi square plus epsilon by 2. This is equal to epsilon by 2 plus epsilon by 2, which is equal to epsilon. So for every epsilon greater than 0, we are getting a n in the set of natural number. That is, for every epsilon greater than 0, there exists capital N in the set of natural numbers such that d of xn comma x is strictly less than epsilon whenever n is greater than or equal to n naught. That is, xn converges to x. Alright, so mark this as 1. Alright, conversely, now let us suppose that this is true and xkn be a arbitrary element or an arbitrary sequence. Alright, so xkn k greater than or equal to 1 be arbitrary simply. Alright, now we are supposing that the if part is true, that is d of xn comma x is less than epsilon for all epsilon greater than 0, that is xn converges to x. Alright, Now d of xn comma x is strictly less than epsilon, xn converges to x basically. Alright, to show that xn converges to xk. Alright, this is what we have to show for all k. We are taking arbitrary. Okay, first of all we have to take the arbitrary sequence. Now d of xn comma x is the summation of 1 by k square or 1 by q square minimum of xk minus xkn minus xk comma 1. So in particular for each k the individual summand is less than this d of xn comma s. So 1 by k square minimum of xkn minus xk comma 1 is less than equal to d of xn comma x, which is less than epsilon prime for epsilon prime lying between 0 and 1. Since it is less than epsilon for all epsilon, so in particular for epsilon dash lying between 0 and 1, this is also true. Alright, and since there is a 1 by k square, so adjust this, we will write epsilon prime by k plus 1 whole square, where k plus 1 is respect to this particular xkn, this particular k. Okay, k plus 1 whole square. This implies minimum of xkn minus xk comma 1 is strictly less than k square by k plus 1 whole square epsilon prime and k, and this is true for say n naught, for all n greater than equal to n naught, say. Alright, where n naught is from natural number, for all n greater than equal to n naught belonging to natural number. Alright, this implies minimum of xk n minus xk comma 1 is less than epsilon prime k square by k plus 1 whole square okay, this is nothing but k square by k plus 1 whole square for all n greater than equal to n naught belonging to the set of natural number. Now k plus 1 is greater than k. This implies k square by k plus 1 whole square is strictly less than 1, and epsilon prime is already lying between 0 and 1. That means this is strictly less than epsilon prime, which is strictly less than 1. So this implies, since the minimum of xkn minus xk is less than 1, so minimum can't be 1 is not less than 1, so the minimum should be xkn minus xk, and this is less than epsilon prime, since k square by k plus 1 whole square is strictly less than 1, so this should be less than epsilon prime, which is already less than 1. Alright, so this is less than epsilon prime, this is less than 1. Alright, for all n greater than equal to n naught from the set of natural numbers. Alright, that is xkn minus xk is less than epsilon for all epsilon greater than 0 for all n greater than equal to n naught in the set of natural numbers. Since this is true for epsilon lying between 0 and 1, so it obviously true for epsilon greater than 1, so it is true for all epsilon. That means xkn converges to xk in R with respect to usual matrix. Alright, since xk and k greater than equal to 1 was arbitrary, we have taken this arbitrary, so that means this is true for all k. That is, we can conclude that xk n is greater than equal to 1 converges to xk for all k is equal to 1, 2 and so on. So mark this as 2 or whatever, and that means we have proved both the part, and hence proved. With this I will conclude the solution of this question. I hope this is clear to all of you. I tried my best, and let me know in the comment section if you have understood this. Okay, thank you.